Okay, let's get started. So today we're going to be talking about performance measurement. So measures. And in today's lecture, we're going to be focusing on binary classifiers. So performance measures on binary classifiers. Okay. Okay, so one of the most popular ways to evaluate the performance of a given learning model is with what's called um, K-fold cross-validation. Okay, so K-fold cross-validation is a resampling procedure used to evaluate machine learning models. Okay, so how does this work? Well, so first you're going to pick some positive integer k, and then for part one, we're going to randomly divide our training data We can also do this on the test data as well. But I'm going to say for our purposes today, we're going to randomly divide our training data into K subgroups of equal size. Okay. So, part two. Oh, I should probably mention subgroups, or we'll call them folds of equal size. So each subgroup is going to be called a fold. Okay. So part two, for each fold, the best way to describe this, we'll say the wording is kind of strange on this, so I guess I'll just go with what I had to put down. The first fold is then treated as a validation set. And the machine learning model is then fit on the remaining k-1 folds. Okay. Then, after the model is fit to the remaining folds, calculate the mean squared error on mean squared error of 1 on the first fold. So what this is doing is you're taking your data, we're going to draw a picture of it here. And suppose you have k is equal to 3, right? So what you do is I'll call this like F1, F2, F3. You suppose we were updating the weights for like the perceptron or something like this. Then we would update the weights here. We would use that data set, that sub data set there to train our model. And then we would evaluate the model that we've trained here on the first fold, and we would call that the mean squared error of 1. Okay? So this is k is equal to 3. And then after you do that, so the part 4, repeat steps 2 and 3 for the remaining k minus 1 folds. So if k was 3 here, then we would next, so if F1, F2, F3. So next we would exclude fold 2 and train our model using folds 1 and 3, and then we would calculate the mean squared error for fold 2. Again, this is fold 2. And then finally, fold 1, fold 2, fold 3, we would exclude folds 1 and 2, fold 3 from folds 1 and 2, train our model on this data set, and then calculate the mean squared error on the final fold 3. Mean squared error 3. And then after you've done this, part 5 would be to say the cross validation score with k of our data set is equal to 1 divided by k times the sum from up to k of the mean squared errors. Okay. And this is a measure of how robust the model is in relation to data that it hasn't seen, right? So you train it here, mean squared error there, train it there, mean squared error there, train it there, mean squared error there. So you're leaving it, you're kind of measuring how sensitive your model is to leaving out certain elements from the training data. Okay. So this is the score, but you can also list this as a, for example, in Python with the scikit-learn, this will return an array where the mean squared error for 1, mean squared error for 2, mean squared error for 3 are in those entries there. So you should probably note that when there are special cases of this, So when k is equal to n, no, when k is equal to n, we have what's called leave one out cross-validation. But typically, k will be something like 3, k, 5, k, 10 are the typical values that you would choose. So let's go ahead and look at this real fast. So give me a moment. Share my screen. Okay, so as I mentioned last time, we are going to be moving towards using Python for the rest of the semester. I think that it's important that not only do you know how to code these from scratch in Julia, but also you know how to work with the various packages in Python to do machine learning tasks. So what we're going to do is we're going to look at the MNEST data set again, and we can say from sklearn dot datasets import fetch OpenML, so open machine learning. Okay, and then we're going to do a little bit of plotting, so we're going to have to use matplot inline and matplot library.pyplot. So let's just go ahead and run this. Oh, I almost forgot one more. What is it? It's import matplot library as matplot library. Just we'll need that at some point. Okay, so let's get the MNIST data set. So we'll say that MNIST is equal to fetch open ML, and then we'll say MNIST 784, and then version 1. It'll take a second to load. It's a large data set, as you all should know by now. Okay, so this object here is acts like a dictionary, so you can access its keys. So we have data, which are this right here. These are our X values. The targets are our labels. And has our feature names and categories and things like this, but we'll only need to really look at data and target. So let's go ahead and do that and say X comma Y is equal to MNIST, and then let's access those keys. So we'll have data, those are our feature measures, and then MNIST target, which are our Y labels. Okay. So if you look at the shape of these things, so this is the 70,000 entry, 784. So these are not tensors like we dealt with in Julia. These are just column vectors. So like that's the shape of it, and this is a x0. It's just a big column vector, and then that corresponds to the label 5. All right. So if we want to look at what these things, like look at the actual images, we can do plt dot image show. and then let's pass it some uh, some x value. So we'll say something like let's look at the 0th one in there. We need to reshape these things into the 28 by 28 grids, which correspond to the image, and then CMAP is equal to binary. So this is like just the grayscale on it. Okay, so BLT-show, and there's our image there. So these are column vectors, and we're just reshaping them into matrices. And we've done this before in Juliet with similar syntax, so hopefully that's not too off-putting for you. Okay, so now let's go ahead and say that the first 60,000 entries are going to be our training data, and the last 10,000 entries are going to be our testing data. So we can do x train, x test is equal to x, so all the way up to the 60,000th entry for x train, and then x test is going to be 60,000 onward to the end of the array. And then we need our y train, and then y test, and in a similar fashion for our y. So y up to 60,000, and then x, sorry, y starting at 60,000 and onward. Okay, now these y's are currently strings. We need to change that, right? We need to change that. So what we can do is we can say, so y train, y test equal to, so do this one line at a time, I suppose. So y train dot as type, and then we're going to change this to np.int8. Just copy that, paste, change this to test, change this to test, and then we need the NumPy module, so I'm going to say import NumPy as np. So it's just getting our data ready. Okay. So now what we can say is like, okay, we want, so this first image is a 5. Suppose we just want to train a binary classifier that predicts whether or not an image is a 5 or not. Okay. So in order to do that, I can say, say y train for 5 is equal to, and then we can say y train equals to 5. Actually, let me make sure of something real fast. Okay, good. So just making sure that the labels are no longer strings, but they are int8. Just making sure. So y test 5 equals to y test equals to 5. So then y, make sure, so y train 5, that's 0, true, because that is a 5, false, so forth and so on. Good. Okay. Okay, so we're going to import a linear classifier from sklearn. So from sklearn.linear classifier, linear model, sorry. Import the SGD classifier. So this is a stochastic gradient descent classifier. And you don't need to know what that does for now, but it's just we're going to use it as kind of like a black box right now, where we just throw in the training and test the training data, and then it's going to spit out a classifier for us. So we can say SGG, so SGD classifier, shorten it up, is equal to SGD classifier. And then we're going to throw in xtrain and actually, no, we don't do that yet. We're going to say random states is equal to 42. We'll discuss that later when we talk about sklearn some more. And then we'll say that, so this is a type, this is a class object in Python, and it has methods, one of which is called fit. So SGD classifier dot fit, and we need to pass in our training data, xtrain, ytrain 5, ytrain 5. So it's a binary classifier, and it's going to say yes or no if it's 5. Okay. Right, so it's training it right now. And then, so every class that you import from sklearn is going to have the methods called fit and another method called predict. So if we do SGD classifier dot predict, we pass it in xtrain 0. What did I do here? I need to reshape it. Dot reshape, and these are 28 by 28. No. Looking. Expected 2D array, got 1D array instead. Xtrain 060. Actually, let me go ahead and say, just to make this a little bit faster, copy, I don't know where the mistake is. So I'm just going to do that. All that code again. I don't see where I would have made a mistake. Just doing this all over again. So we should have a predict method. All of these will have predicts. And we can do xtrain 0. Let's see what happens here. There seems to be just copy this one. I think that might be a problem. Oh, no, this is the problem. Yeah. So 1 second. Oh, 1, -1. Ah, that's all I was missing. This just needs to reshape it to the correct size. We saw all the errors I was getting. They were errors involving the shape of the input. So I should have caught that sooner. Okay, so what we're going to do is we're going to look at k-fold cross-validation. So we're going to say from sklearn dot model selection. We're going to say import cross-validation or cross-val score. Okay, and then we're going to say cross-val score. And we're going to pass in our model. So SUV classifier. And notice that, okay, so yeah, it's our model. And I'm going to say X train, Y train 5. And then we're going to choose K to be 3 in this case. And our scoring is going to be accuracy. Okay, so it's take for a while to run. It's computationally expensive, but as compute power has increased, it's become easier to evaluate these things. Okay, so as I put on the board earlier, we have our mean squared errors calculated on the fold that was left out and where the model was trained on the other instances of data. So if we look at this, we see that we have an accuracy of something like, maybe I can just do, so say, so this is a numpy array, so np.array, and then I'm going to say mean, yeah. All right, so here we have roughly 96% accuracy on determining if a image is a 5 or not. But is this good or bad, right? In fact, we really need to think about, well, we have this data set, how many of those data entries are 5s? So the textbook that I'm using is a pretty good, pretty clever example of how to compare this with just like the most absurd classifier that you can think of. So let's say from sklearn dot base import base estimator. And then we're going to design our own classifier. And we're going to call it the never 5 classifier. So class never 5 classifier. And we're going to pass base estimator. Okay. And there's going to be 2 methods in this class. So the fit method takes self, some x data, some y data, we'll say none, and then just going to return self. So fitting this model doesn't do anything, just returns the same model. And we're going to say def predict takes itself, and then some x, 10, and then we'll say return np dot zeros. Then we got to give it the dimensions, length of x 1, so it's all zeros, and it'll be type equals to bool. So what does this predict method do? Well, it basically predicts that the digit is never going to be a 5. Right? It's all zeros, and so it's always false. It's always a bool type false. So this thing just always says that for any data set that you give it, it's never a 5. That's all this does. So then we can say, okay, let's look at our never 5 classifier equal to our class that we made. We don't pass it anything. Okay. And then we'll say, okay, let's do the cross-validation score with this classifier. So never 5 classifier. And we see that here, it's roughly 90% accurate. Well, what's happening here? Well, the reason for that is, even though this thing always predicts that it's never a 5, no matter what you pass into it, roughly 90% of the images are not 5s. So it's saying that it's 90% accurate because 90% of the images are not 5s. But it's surely not a good binary classifier, right? So there's another way to look at the performance of a given algorithm that might take into consideration these very specific cases where there's very few 5s in there. So if you have a classifier that's predicting not 5s, it has a high k-fold validation measure. And that will be called the confusion matrix. Okay, so let's go ahead and look at that. Okay, so the confusion matrix. Okay, so the general idea behind this is to count the number of times times instances of class A are classified class B. So vaguely speaking, that's what we're going to do, and we're going to fill in the entries of a matrix as follows. So with our example with our 5s and not 5s, so I'm going to write this out first. So each row represents an actual class while each column represents a predicted class. Okay, so for example, we can have like here, this is like, so predicted, predicted class B, maybe, and then this is predicted class A, and then actual class A, actual class B. Okay, so for example, let's look at like handwritten digits like 3, 7, 9, 2, 1, 6, right there, and then 5, 5, something like this. So it might be easier to say that the two classes are either -1 or 1. Like think back to the perceptron. So we'll say, we'll do that. So this would be like predicted class -1, predicted class 1, actual class -1, predicted class 1. Or the actual versus predicted for a given model. Okay. So so here we would have what's called true negative. Here we have false negative. Here we have false positive. And then here we have true positive. Okay. So basically, here is the number of elements in our data set that were negative, were a negative class, -1 class, and our model predicted -1 class. So this counts the total number of ones we could correctly predicted negative. Here, this counts the number of times we classified as positive when it was negative. So that's false positive. That should have been a negative. Right? And these are just like images. Like think of these as like images that we're putting in there. So like really inside of these cells is going to be a count. So here in this entry here, these should have been predicted positive, right? But they were predicted negative. So those are false negatives. And in here, these are true positives where they were positive, and we also predicted with our model that they were positive. Okay? So a perfect classifier would have only true negatives and true positives. There'd be a 0 here and a 0 here. There wouldn't be any false negatives or false positives. Okay? Okay, so let's go ahead and kind of fill these in. Right, so I'm going to use abbreviations, so true and negative, false positive, false negative, and then true positive. Okay. All right. So this is a grid of information. These are a grid of counts, basically. But from this, we can infer a few measures of our model. The first being precision, which is equal to the number of true positives divided by the true positives plus the false positives. This will be our precision measure. And then our recall measure is going to be the true positives divided by the true positives plus the false negatives. That's our recall measure. Okay? And then finally, we have what's called our F1 score, which is equal to 2 times the precision times the recall, all over the precision plus the recall. Okay. Now, this F1 score is really a harmonic mean of the precision and the recall, which means that it basically, you only get a high F1 score when both precision and recall are high. Okay. Okay. So let's look at the confusion matrix for our given problem. So, screen. Okay, so these things are pretty easy to develop. So let's say from sklearn dot model selection, import cross validation predict, and then from sklearn dot metrics, import confusion matrix. Okay, so y train predict is equal to cross val predict, and I'll explain what this does in a moment. But we basically pass in the same parameters here. Except we don't need scoring here. Okay. So what this does is it does cross validation, but now so cross validation with k is equal to 3. But instead of computing the mean squared error, it's going to count the number of instances where a prediction was made. So once this once this terminates, I'll show you what it looks like. So y train predict. So it's just it's instances. So this was predicted to be a 5, this was not predicted to be a 5, so forth and so on. So once we have that, we can pass that into the confusion matrix. So confusion matrix, and we give it the training instances, and then we give it our predicted instances. And it's all we need to do to make this 2x2 matrix that I put on the board a second ago. Okay, so we see that the true negatives, we got this many, but there's this many false positives, and then this many false negatives, and this many true positives here. Okay. So, okay, so this is the confusion matrix, and then we can look at the recall score and precision score as well. So from sklearn dot metrics, import precision score, and import the recall score. Okay. And then we can look at these separately. So we can say precision score for Y train 5, and then Y train predict. And then we can do this again with the recall score. Okay, so what this is saying here is that this precision score, so when it claims that the image is indeed a 5, it's only 79% accurate when it does that. So when it claims that it's a 5, it's 79% accurate. And then here, this is when it isn't a 5, it detects that 70% of the time. So this precision recall gives you quite a bit of information about what you can expect from your model when you deploy it on your testing data, right? And sometimes you may want your precision to be higher, and versus sometimes you want your recall to be higher. But it turns out you can't have both of these high at the same time. If precision increases, recall is going to decrease. If recall increases, precision is going to decrease. And that's something that we can discuss next time. Okay, so I'm going to go ahead and end it here. We're going to finish up performance measures next time, and then we will start a new topic next week. So that'll be it for today. Please, everyone, if you can, I still haven't seen everyone's GitHub repositories. I really want to take a look at them, so please get those to me when you can. All right, that'll be it. I'll see y'all on Wednesday.
Thank you, Dr. David.